All right, so I want to talk a little bit more about this Markov chain business, and then also get into chapter 4 point whatever we were on last time. I forget. It doesn't matter. And continue on from there. Yeah. Yes, there it is. 4.6. That's the one I was thinking of. Anyways, whatever. So that's what we're going to be looking at today a little bit, and kind of going from there. Is my plan. 4.6? Whatever. I don't know. Anyway, so last time we mentioned in class the Markov chain. A Markov matrix is always a situation where you're going from to. Okay, from to. That's what you're doing. Okay, so you're going from A to A is 0.7. From A to B is 0.3. From B to A is 0.2. From B to back to itself is 0.8. This is a Markov matrix. Notice the sum of this column is always 1. Sum of this column is always 1. It's always true in a Markov matrix. Now, something to think about in this guy is this. Whenever you do a Markov matrix, if you were to find his eigenvalues, you will find that you get 0.7, 0.2, and 0.3, 0.8. You get that. You get 1 and 0.5. It turns out that every Markov matrix will always have 1 as one of its eigenvalues. And the other one will always be less than 1 in absolute value, if that makes sense. So 1 lambda is always 1, and the other lambdas, the absolute value is always less than 1. Okay, that's a fact. Always going to be true. Okay? So just keep that in the back of your head. While we're here, I'm going to go ahead and find the eigenvectors on this fella. And there they are just for fun. Okay, again, we talked about this last time. The second one is obviously negative 1 and 1. The first one, if I do 0.83 divided by 0.55, you see I get about 1.5. If a guy were to flip that, divided by 0.83, you get about 0.66. Now I just point this out. We will be looking a little bit more at our eigenvalues, or vector rather, relationships later on, but just so you remember that that's happening. Okay. Now the idea is, here we are, boom. Okay, and so these are situations where you have people, and you have a certain number of people, and so in this case, they were either using brand A or they were using brand B. 120 were here, and initially 80 were here. And so when you do this again, we're gonna have this. This is a transition matrix here. This guy here is this initial value piece here. His name is it's the state. It's the it's the initial state vector. What do they call? I can't remember what they call here. Hang on. Yeah, anyway, it's the initial state of where we were at. Okay. Now, what ends up happening is, as we do this, that's where we started, and then over time, things are going to change for us. Okay. So when I do this, I'm going to get. First of all, it's pretty clear that when I do this, I'm going to get a I'm going to get another 2 by 1 or another 2 by 1 vector when I'm done. In other words, I started at a certain place and I ended up somewhere else. Okay, and then from there I'm going to go to the next one, if that makes sense. Oops, shoot. What are you doing, stupid? 0.3, comma. Oops, 0.2 rather. And so what we're going to be doing is we're going to be like, okay, well, here I am now. Now what? Well, now I'm going to do it again. And then what now? Well, I'm going to do it again. What now? Well, I'm going to do it again. So I'm going to store this guy as A just for fun. And then I'm just going to take A times. And I'm going to multiply it by this initial state vector, which is 120, 80. And then I'm going to go ahead and transpose that. I just think it's easier to put it in thusly. And I get 100, 100. So now there's 100 in each. Now what? Well, I'm going to take A times that, yeah? So alpha A times that answer. And I get that. And if I do it again, wait, but aren't you just taking A? Exactly, friends. We're going to take A to the k power, right, times this initial guy. So our initial vector. Okay. What I'm left with eventually is going to come to steady state. Steady state. That's going to be a big deal to us. But a couple of things. Why did we learn about squaring or cubing or whatever vector matrices? For right here, right now, baby. This is one example of it. If we're doing it old school, we're not doing it old school. Let's let this happen 15 times. You with me? Times parentheses, I don't know, brackets rather, 120, 80. And again, we're starting off with that initial 1 because that's all that counts. That's all that matters. And so there you go. Eventually, we're going to get back to, I don't know what just happened. Where did the T come from? Oh, that's right. Transpose, that's right. Yeah, and so basically when you get back to it, you'll get back to 80 and 120. It's shifting completely the opposite direction. Now, that's interesting. I just for fun, what is 120 divided by 80? Oh, poop. That's not right. Hang on. 120 divided by 80. Oh, that's interesting. Well, that's 1.5. That's weird. Oh, that's interesting. Let's reapproach that, shall we? So I'm going to grab this guy here, bring it down, and I'm going to do 0.83205029438 divided by 0.55. Where did I leave off? 4700196225. Hey, look at that! I get 1.5. Shut your mouth. Is that always true, Jay? Yes. And so, interestingly enough, the eigen vector rather that corresponds to 1, which they refer to as the unity eigenvector value, will tell you what the steady state solution is going to look like when we're done. That's going to always be true. Okay, which is kind of cool. Yeah. Sorry about that. I love it when the stupid little home screen pops up and it's stupid. Now, we are going to look at a couple other examples. Now, that is from section 3.7 is where I'm looking at currently. I'm going to do one of these guys from section 3.7. And then after I look at that, we are going to, what I should say. So when we do this, we're going to do a couple examples of this, and we're going to see what happens in the long run. Now, for instance, this guy here. Suppose you had this one. You met this thing in a dark alley. 0.3, 0.3, 0.4, 0, 0.5, 0.5, 0.2, 0.3, 0.5. Notice, again, first of all, it has to be a square matrix. Why? Well, for one thing, you have 3 things, and then you can go 3 places from 3 things. We can go from A to B to C. Okay, clearly from A to B looks like, from A to A is 0.3. Okay, A to B is 0.3. A to C is 0.4. Nice. But then from A there isn't one. And then from B to B it's 0.5. From B to C is 0.5. And then from C to A is 0.2, and 0.3, and 0.5. Okay, that's what we're doing. That's what we're talking about here. And so, kind of keep that in the back of your head, okay, as we do this. First of all, is it a transition matrix? Yeah, of course it is, because the columns sum to 1. So if I had a situation where we have 60, 120. What will happen in the long run? Where will we steady state to? So what I'm going to do is I'm just going to pull this up. We're going to have a look at our eigenvalues real quick. Oopsie daisy, is that right? Yes, there it is. Eigenvalues of 0.3, 0, 0.2. 0.3, 0.5, 0.3, 0.4, 0.5, 0.5, bracket dot dot. Now, no way. There is a unit. Oh, So there's a unity vector of 1. Yes. The others are 0.2 and 0.1 as promised, less than 1. That's pretty cool. Now, let's take this fellow. Let's lose this. Let's lose this. Da, 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 da. Let's go ahead and set him, store him as A, just for fun. And then I'm going to go ahead and multiply A times, I'm going to take A to the 100th power because I feel like it, times this fella, 60, 100, 20. Boom. Boom. Second math matrix. Yeah, da, da, da. And lo and behold, we get, you can do it. We get that, baby. Now, if you're playing along at him, I'm going to do it this way. 87.5 divided by 25 is... Dun, 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 dun. No. 3.5. You're going to get 67.5 divided by 25. 2.7 and 1. Okay. Now, just for the sake of argument, okay, I'm going to divide them all out. So I'm going to do 1 divided by 3. So I do it a couple different ways. It doesn't really make any difference. I could have done it this way. I could also have just done this up here. Take this guy right here, whatever it is, and I could have just done the square root of. Well, I could do dot product with itself too. So the square root of 25 squared plus 67.5 squared plus 87.5 squared. Oops, squared. And whoopsie daisy. Whoops. There it is, 113. You're like, well, what am I going to do with that? Well, what is this guy divided by that guy? That right there. Now hold that thought. First of all, what do you know about that? That is by definition a unit vector, correct? Okay, now hold that thought for just a moment. Okay, hold it. Are you holding? Now let's go find the eigenvector values rather. Vectors, eigenvectors of A. Well, now you shut your mouth. You shut your mouth. Is that always true? Yes, 100%. The eigenvector that corresponds to the unity eigenvalue, that is the 1, that will be over time what we approach. Over time, the steady state solution will approach that ratio. Okay? And so you can actually kind of cut to the chase when it's all said and done. Okay? Now you're like, so if you're like me, and you're like, what is that? What is that? Exactly. Well, if you wanted to, percentage-wise, now, those are in a ratio format. A 0.22 to 0.59 to 0.77 ratio. If you're like me, you're like, give me a freaking decimal, please, Jay. No, I'd love to. So I'm going to use the whole numbers that we had, and the whole numbers were 25 plus 67.5 plus 87.5, which you said was 180. 25 divided by 180 is, so in other words, you moron. So you're going to have about 14% in the first one. You're going to have 67.5 divided by 180. You're going to have about 37.5% in the next one. And then, of course, the last one is 87. And you're going to end up with about 49% in that one. Okay? And if you do that, you're like, oh, that's what it's going to come out. Eventually, we're going to come out to those percentages. That will always happen in a Markov chain scenario. Always. Okay? Always. Now, let me pause you for just a second. All right. So in 4.6, we're going to be talking about some applications in the Perron-Frobenius theorem. Okay. And so check it out. if P is an n by n transition matrix, P is an n by n transition matrix, one of the eigenvalues is 1 always. Okay? And then part that was theorem 4.30. So theorem 4.31 is, again, if this is true, you have an n by n transition matrix, the other lambdas will be less than or equal to, well, all the lambdas will be less than or equal to 1. Okay? Yeah, and so then it's a yeah, so then there's two definitions. A matrix is positive if all of its entries are positive. And if a square matrix is called regular if some power of it is positive. Okay, so for instance, this one here is a positive matrix, so 0.2, 0.3, 0.6, 0.1, whatever. That's a positive matrix, okay? And if this guy were negative, you're like, whoa, it's not a transition matrix. I get that. That's right. And you're like, whoa, what do you mean? Well, hold that thought a minute. Let me backtrack up here. Suppose you had again, a transition matrix. And if P is regular, now regular simply means it's a square matrix. So keep this in mind. A square matrix where some power of it is positive. So this guy right here is not a transition matrix, but it is regular. Okay, so that is some power of it is that. So two things must be true here. So number one, the lambdas all be less than or equal to 1. And then B, or part 2 rather, if P is regular and lambda does not equal 1, then the absolute lambdas are all less than 1. Okay, and so that can happen. That again, that is not a Markov chain transition matrix, though. Okay, so just kind of keep that in the back of your mind. That's not going to be cool for us. Okay. So P is a regular n by n transition matrix if P is diagonizable. And then the dominant eigenvalue is lambda equals 1. Okay, so check this out. This is kind of a big deal. So this is a lemma. Okay, it's a part of a theorem. It kind of follows from a theorem. Let P be a regular n by n transition matrix. If P is diagonizable, and we talked about that last time. If P is diagonizable, what does that mean? Well, it means I can put it on the diagonal situation like there, and then, of course, I can actually go ahead and square the thing out, right, or cube it or whatever, which is kind of a big deal. Then the dominant eigenvalue, lambda 1 is equal to 1, has algebraic multiplicity of 1. And that's pretty obvious because it's the only one it can be. We are only going to have this transition matrix, when it works out correctly, we're going to have the 1, and the rest of them are all going to be less than 1. Okay. Pretty easy to do there. That's a big deal. If we cannot write that in that diagonizable format, then we cannot raise it to a power, right? That was the whole point of that scenario. And the reason it was diagonizable, if you recall last time, is because that means our rows and our columns, whichever you want to look at it, were independent, which means that we had, if that's true, then that means we have independent eigenvalues. Okay, because remember that's how we get our P matrix, okay, from when we were doing this before. And so we have independent eigenvalue vectors. Okay, that's a big deal going forward. Okay. Now this is also kind of a big deal. Okay, this guy right here, and the reason. Oh, by the way, the reason these transition matrices have to work out is because they are decimals. That's why they have to converge. Because remember, we're raising it to a power, so they have to converge. So P Let P be a regular n by n transition matrix. Then as k goes to infinity, p to the k approaches and n by n matrix whose columns are identical, each equal to the same vector x, each identical to the vector x. Weird, huh? This vector is the steady state probability vector for P. This vector is the steady state probability vector for P. What do you mean? Well, let's find out. Here's a nice one on my calculator right here. How exciting for us. What if I were to take A and I raise it to the, 100th power, for instance? Oops, not the 0 power. That's going to be problematic. Let's do it to the 20th power. Okay. Oh, shut your mouth. Look at that. Whoa, it's, oh, shut up. That's 14%, 37, no way. That's exactly what we're saying, friends. Over time, that's what's always going to happen. That's pretty cool. And you're like, well, wait a minute. Is that why? No, check this out. Is that why when you multiply it, you always get the same answer? Yes! Because there it is. Whatever was going in, it's coming right back into the thing. Okay? And it's pretty slick, pretty neat, pretty exciting, honestly. It's just how the game is going to be played. That's always true. Okay? In essence, what you're doing is back when we did eigenvalues the first time, we said A lambda is equal to A lambda is equal to come on, Jay. No, AV, I'm sorry, that's it. AV is equal to V lambda V, right? That's it, right? It's just a constant times it. And that's the idea, right? That's the idea. When we do these problems, you're like, oh, that's weird. Yeah, in essence, we are making this guy, that guy becomes just a column. It becomes, in this case, 3 columns of the same eigenvector over time, okay? Over time, that's what it's going to approach. What is that? That is the eigenvector that you had on your very first, your dominant one. That's what it becomes every time. And again, if you look at it, what does that tell you? Those are the percentages: 14%, 37.5%, 48.6%, whatever. And that's how this always will work in a Markov chain. Let P be an n by n matrix. X is the steady state probability vector. P for P. Then for any initial probability vector, the sequence of iterates of xk approaches x. Oh, okay, what does that mean exactly? So let's do this. So let P be a regular n by n transition matrix. Yep. With x, the steady state probability vector. For P, okay, as in theorem 4.3. So that's exactly what we just talked about, okay. Then for any initial probability vector, x naught, the sequence of iterates x sub k approaches x. Nice. What do I mean by that? It means that every time I keep doing this and raising it to a power, I'm going to get closer and closer and closer and closer to that. Does it make sense? So as I'm punching that through, the first time it was getting, not as much. Second time's closer. Third time, fourth time, fifth time. By the 20th time, the 30th time, you're like, Jesus, they're almost identical. And for all intents and purposes, they are. We've already kind of shown that to be a true statement. Okay? Yeah. So kind of fun, kind of a good time. So anyway, the other thing in section 4.6 I just want to introduce briefly is another use for eigenvalues and eigenvectors. And so this one is kind of fun because it has to do with solving differential equations. So this one right here, for instance, is a systems of differential equations. And if you had 3x plus 2y and y, oh, darn it, just a minute, I'm going to pause you again. There you go, like that. So if you found this guy and you're like, oh, I want to solve this, and if x of 0, the initial population was 10 and y of 0 was 6, cool. Then what you can actually do is you can actually find the eigenvalues and eigenvectors here, because what we believe to be true is that all of our solutions are of the format e to the lambda 1t plus e to the lambda 2t with constants in front of them. And you're like, well, what constants? Well, now, hey, it's going to have to do with obviously satisfying these conditions. And you're like, well, yeah, okay, but that's 2 conditions, Jay, but this is 4 unknowns. Yeah, I know. Check it out. Because they're related, how cool is this? There is a ratio from top to bottom. X might be twice as big as 1. No way. Do you mean the eigenvector? You know it, pal. And so what we often do in these classes is we say, instead of xy, we say x1, x2. So we say it's the x vector is equal to some constant times v1 times e to the lambda 1t plus c2 v2 e to the lambda 2t. And that's how we typically write our answers, okay? And so when we do this problem, we're like, okay, well, let's punch it out, find out what we're doing here. So boom, boom. There we go, nice. And 3, 2, and 4, 1. There we go, bam. So 5, -1. Again, I've said this before, I'll say it again. I do not want to run into a population that's growing at e to the 5. We just don't want to do it, or e to the 5, because that's going to be scary. So here's the deal. So we come back into this guy, and you're like, oh, okay, well, what are the eigenvectors? And so they are 1, 1, and 1, -2. 1, 1, 1, -2. -2. So there's going to be, give it to me, you hippie. What are you doing, bro? Bro. So 1, 1, and 1, -2. But check it out. There's going to be a C2, a C2, a C1, and a C1 that we're going to be solving for. 1, 1. 1, -2. So when I do this, what that really means is when you plug 0 in, you're going to get 10 equal C1 plus C2. And when you plug 0 into Y for T and for Y there, you're going to get C1 minus 2 C2. If a guy subtracts, you get 4 is equal to 3 C2. So C2 is equal to 4/3. C1 must be equal to 26/3, I guess. Right? Right. Which means that our final answer is going to be, check it out, 26/3 for both of these guys. Well, that's a 1-to-1 relationship. I know, right? And then the next fella is going to be 4/3. and negative 8/3. Whoa! 4/3 and negative 8. That's a 1 to negative 2 relationship. Yeah, I know. Isn't that cool? Boom, done. That is where I like to use, where I use most of my eigenvalues in my daily life. That's not true. I don't ever use eigenvalues in my daily life. That is where I use them the most, okay, in my worldview. Okay, here's another one. Dun, dun, dun. Okay, where was I going with this? I got sidetracked. Sorry. Oh, that's hot. There we go. And then x of 0 is 4 and y of 0 is 10. Sweet. There's something sticky on my computer. Weird. Anywho, here we go. So I almost reached for my other computer. There we go. So we are going to find the eigenvalues for 3, negative 3, 2, 4, and lo and behold, Judas Priest. I typed something in wrong. I hope I typed something in. Oh, I know why. It's supposed to be positive 3 up here. Positive 3. There we go. Don't freak out. Yes, there can be imaginaries. No, we're not going to probably get into that whole bunch in this one. There, 6-1. Yay! So, we believe I can fly. C1 times something, e to the t, plus C2 something, e to the 6t, baby. There you go. Okay? So then the question then becomes, well, all right, what are the eigenvectors? And we get that 1, 1. And I feel like I should know this one now because I feel like we've done that enough. That's a negative 1.5 to 1. Right? We've done that one a bunch tonight, I feel like. So if you plug in those, you're going to get C1 minus C1.5 C2s is equal to 4. And you're going to get C1 plus C2 is equal to 10. And if you subtract, lo and behold, you're going to get negative 2.5 equals negative 6. Oh, I can't do math today. 6 divided by 2.5, 6 divided by 2.5 is 2.4. So you're going to get C2 equals 2.4. So C1 must equal 7.6. Okay, so my final answer would be x equals 7.6 e to the t minus 1.5 times 2.4. 1.5 times 2.4 is 3.6 e to the 6t. And look at that. When you minus them, what do you get? And then y equal 7.6 e to the t. That's a 1-to-1 relationship. Sure is. Plus 1 C2, so 2.4 e to the 6t, and lo and behold, that happens to be 10. So that's exciting. That's how we solve those, okay? That's what you're going to be doing primarily in section 4.6. Those are the parts that I've picked out that I would like you to look at. So that's that business there, and then we'll just move on.